Welcome everyone to the Air-Sea Fluxes from Space webinar series. Today we have Juan Crespo from JPL, who's going to talk about CYGNSS observations of air-sea interactions in extratropical cyclones and atmospheric rivers. And I'll let you get started, Juan. I think people are still getting on, so you can
No
start
worries.
gently.
Thanks, Sarah. Thank you for having me. So I recently gave a seminar 2 weeks ago down at Purdue. So I think it's okay if people are a little late because the first couple slides are very, very introductory. I was like, wait, like, you guys know the importance of air-sea interactions. I don't need to justify that to this crowd and why we need to observe it. So I did trim that down a bit, I will say, but there's probably still going to be some of that general introductory items. But yeah, I think this crowd is okay missing the first few minutes there. So as Sarah mentioned, my name is Juan Crespo. I am with UCLA as a research assistant and an affiliate at the Jet Propulsion Lab. And the work that I'm presenting here today is kind of culmination of what I've been working on the last few years with CYGNSS. So that's the Cyclone Global Navigation Satellite System. Developing a lane sensible heat flux product, just to, as a way to show the importance of why we need to be able to observe the air sea flux from space and, as a bit of a justification for future missions that could be able to provide then better observations from what we have from our current satellites. So the work that I'm presenting here today, I've also been working with Catherine Naud of GIST, Shakil Asharaf of UCLA and JPL, Rosa Luna Nino at Scripps, and Derek Basalt at JPL. So just very quick general introduction. When we talk about extracyclones, we know that there are these large um, synoptic systems in the mid-latitudes driven by temperature and moisture gradients. And we all know very well that they tend to occur much more often in the winter hemispheres and produce the majority of the precipitation that we see in the mid-latitudes and temperate regions. And we've had a very good synoptic understanding for over 100 years now, starting with the Norwegian cyclone model and the Shapiro-Kaiser model as well about 30 years ago. And with this now, with our work that we've been doing with extracyclones, we've started looking a bit more into atmospheric rivers because oftentimes ARs are associated with extracyclones. Of course, they can occur on their own without an ETC, but oftentimes in mid latitudes, we kind of see the two of them working together. And of course, we all know very well they can provide bulk of precipitation on the US West Coast and in other parts of the globe, but they can also be associated with some major flooding and mudslides, especially in areas that have fire scars. Last year, we currently live in Michigan now for my spouse's job. But last year, when we're still living in Los Angeles, our car got inundated by one of the atmospheric river events that happened in January. So kind of do take it a little personally. I know there's a few people here from San Diego and Scripps as well. So you guys very much know the impact of ARs. So as you said, when we look at atmospheric rivers, we often see them associated with extratropical cyclones, usually within the warm sector and ahead of the cold front. And of course, at least when I mentioned this to the crowd at my seminar a few weeks ago, we should not be confused. The AR is not the same as the warm conveyor belt. They can be associated with each other, but they're not the same thing. As the warm conveyor belt transcends or transports moisture upwards into the extracyclone. However, when an ETC does have an AR associated with it, the extracyclone itself that is often stronger and has more precipitation. So it's important for us to be able to look at these two together. Let me just hide the little thing. There we go. All right. So as I said, we've had a very good understanding of extracyclones and atmospheric rivers at the synoptic level. But when it comes to understanding the mesoscale processes within them, there's still a little bit of unknowns, especially when these are occurring out over the ocean where we do not have many in situ observations. So this is where we want to bring in more satellite observations. Specifically, what I want to look at is how do the air-sea interactions within the boundary layer impact ETC development, AR development, and how does that relate to the cloud and precipitation development that we see, not just in the static scale, but in the mesoscale and submesoscale. And then one thing we also want to look at now is, how do air-sea interactions possibly play a role in developing clusters or families of extracyclones and atmospheric rivers? So In the seminar that I had earlier, what we want to drive is how can we be using existing and new satellites to better understand what is happening within ETCs and ARs at these smaller scales, and how does the air-sea interactions play into their genesis and evolution. So again, like I said, this is a very basic introduction. I think for this crowd, I do not need to justify the importance of surface heat fluxes. We know that they can increase the volcanicity and instability within the marine boundary layer. And oftentimes we do see rapid cyclone intensification over the areas such as the Gulf Stream, of the Kuroshio Current and Kuroshio Extension in the Western Atlantic and Western Pacific Oceans. So while we do see strong air-sea fluxes associated with ETCs and ARs, there's still, at least from my infrared, quite a lot of debate on exactly how much of an impact they have. So, we can see there are some papers that say, yes, the surface heat fluxes directly lead to a stronger and more intense exocyclone. There's some say that it's, just purely a correlation, that, the strongest surface heat fluxes is just a sign of a strong cyclone. And there's even some indication that maybe the stronger the fluxes are, the weaker the cyclone becomes. And we'll talk a little bit more about that as well from what we've seen from our observations. And then recently there have been some idealized modeling studies showing that, the strong surface heat fluxes within the primary extracyclone atmospheric river don't necessarily impact that primary cyclone, but they are actually transported upstream and intensify extracyclones and atmospheric rivers within a family and make the upstream cyclone stronger as well. So, one thing that most of these all agree on is that, more observations and more consistent observations are needed to better understand the complex dynamics of what's going on here. So as has been discussed in this group many times, that, what we're trying to do is, we're trying to tackle the problem of estimating these fluxes from space. So we know that currently our satellites cannot observe these fluxes directly, but we can observe the components of temperature, humidity, and wind speed. So scatterometers and microwave instruments in mostly polar orbits, they've been very good at this, but they can still have some gaps in their observations. So one thing I've been trying to work on is filling in the gaps. So when we don't have observations and scatterometers, what kind of instruments can we use to fill in the gaps when we don't have scatterometers and when we don't have in situ observations? And so this is where I wanted to bring in Cygnus, because this example here, the observations are from an SSMI one of the SSMI instruments. And you can see that, it's missing some parts and so this is an actual cyclone that occurred in January 2018, and we're seeing it's missing some parts of this ETC, but underneath of that, we see the observations that Cygnus provides. So while we have, these observations from scatterometers, in the gaps where we don't have observations on them, we can start using other satellites such as Cygnus. And so this is where I kind of see the role of the work we've been doing, is filling in those gaps. And, we're having some synergy with these other products as well. So to recap about Cygnus, so it is a constellation of 8 satellites. Now it's currently down to 7 that observe GPS signals reflecting off the ocean surface. So these produce the specular points, and this is what we have. You can see the types of observations we have from Cygnus here. So you get these individual dots. So it's not the traditional swath that you see from other satellites. So each observatory can observe 4 specular points per second. So, multiply that out by all 8, that's about 32 observations per second for the entire constellation. And so with this, they estimate the surface wind speeds based on the scattering. And the advantage with Cygnus is that it does use the GPS channels, which do not attenuate in precipitation, which is why your GPS does not go out in the middle of a thunderstorm. And one advantage, so Cygnus was launched as a tropical mission, primarily to observe tropical cyclones. The ability to observe tropical cyclones by Cygnus is up for debate, but nevertheless, for us, in our purpose, even it does provide near daily coverage of the tropical and subtropical oceans. So this is what an example of a full day of data provides with Cygnus. So the advantage with it is that you get rapid revisit times, especially the closer you get to the equator. And when you get closer to the extratropics, you get observations about once per day, but you're getting observations through about like a 6-hour range as well, because the the satellites come one after the other in the constellation. Now, of course, we are talking about the extratropics, and we're trying to use a tropical satellite here. So I can understand, some of the hesitation about that, but Now, one of the reasons we are able to justify this is that when we look at where we're seeing the strongest surface heat fluxes across the globe over the oceans, they actually tend to occur closer to the tropical and subtropical regions. So this is a BAMS paper from Juan in 2007 showing the climatological averages in February. So in the winter season in the northern hemisphere in August, so winter season in the southern hemisphere. And if we just overlay where Cygnus is observing, about roughly, we see we can capture most of the Kuroshio current extension, a good portion of the Gulf Stream as well in the winter seasons, and then some of the higher surface heat fluxes are observed in the southern Indian Ocean and around the coast of Australia. And we just sort of, I'll be able to show this later, but we are able to capture a little bit as well some of the high surface heat fluxes off the coast of South Africa as well. So because we were in this range of where the typical surface heat fluxes occur over the oceans, this is where we wanted to start using the Cygnus wind speeds to estimate the latent sensible heat fluxes. So for this, we use the level 2 surface winds from Cygnus to estimate the fluxes, and we're using the Core 3.5 algorithm. For temperature and humidity, because Cygnus only provides the wind speeds, for now we are using ERA 5 to fill that in, just because it provides consistent estimates of those observations every single hour. So we don't have to worry about, if we use other satellite observations, we're not worrying about, the time being off and such when we want to make those estimates. Previously, we had used MERA 2, but we switched to ERA 5 about 2 years ago now, because ERA 5 does provide a much better resolution, and also the data is available typically within a week, whereas with MERA 2, we were often waiting a month or two just for the data to become available. So even though the Cygnus product is not meant for operational data or operational analysis, nevertheless, if there's a cyclone or atmospheric river that occurred in January, you would have to wait till the end of February or March to be able to really to use the observations from it. Whereas now with ERA 5, you can turn that around much more quickly. So I don't think I really need to discuss too much about the Core 3.5 algorithm to this group, but just to refresh our memories, it is validated up to 25 for wind speeds up to 25 meters per second, just because at that point, the drag coefficient breaks down, and you need to be able to better estimate the impact of sea salt spray at those higher wind speeds. And with that, we just do not have that ability right now. So for our Flex product, we do put a QC flag when winds are above 25 meters per second, just to warn the public, whoever uses this data, to be cautious when using that, because the estimates are probably not accurate at that region. But yeah, so with this, we're able to estimate latent sensible heat fluxes at every single specular point. So this is the current product that we have. So this is version Science Data Project version 2.0 that's currently out through the PODAC. So every frame here is 1 day of data. So I can't see the time because the zoom controls are hiding it, but I think we're right now in Southern Hemisphere winter. So you can see the large heat fluxes that you typically see in the region. And then as we shift to Northern Hemisphere winter, you start to see the large latent sensible heat fluxes off the coast of Japan, off the coast of the United States. So again, even though Cygnus is a tropical mission, we are able to observe these large fluxes occurring. We did validate our data with various buoys throughout the tropical and subtropical oceans. We see that when we're at the lower flex values, we're very close to that 1-to-1 line. With sensible heat fluxes, we're very close to right at 0, just because over the oceans, our sensible heat fluxes are much lower, and sensible heat fluxes aren't driven by wind speed compared to latent heat fluxes. But nevertheless, we are close to that 1-to-1 line. There is some variance going on there, and I will say that when we do get higher up, we do tend to underestimate the fluxes just a bit, mainly because Cygnus is actually underestimating the wind speeds at higher wind speeds. So this is what I was talking about earlier. One of the issues with Cygnus has been unable to, once wind speeds are above 20 meters per second, there's still some calibration and validation issues that are still ongoing with the project. So that can lead to us getting some lower fluxes in those regions as well. But that is, slow. Thankfully, that is slowly getting better. And of course, since our fluxes, we do have to provide the QC flag for 25 meters per second. It's something we're also working on as well. So it's an issue that we want to tackle on both sides. But nevertheless, it shows that what we're able to do when we're able to pretty well fill in the gaps between the in situ observations that we have. So again, even though this is a tropical mission, we are able to observe the large fluxes occurring in the Western Pacific and the Western Atlantic, as well as in parts of the Southern Hemisphere in the winter season. So now that Cygnus has been in orbit for over 5 years, we're able to produce this climatological analysis here. I do have to include 2023 for June, July, August, but I would likely the results would be pretty similar, although we do probably have to factor in an El Nino there. But yeah, we can see, even with this product, we can kind of see some of the waves occurring in the Kuroshio extension, and then this, nice feature with the Gulf Stream. I haven't quite analyzed, these individual troughs and ridges within there, but yeah, that might be something worth exploring later on. But now that we have these observations, we want to see how well does it do observing actual cyclones and atmospheric rivers. And thankfully, it does a pretty good job, I would say, for what we have. So this is from a paper we published about 2-3 years now. So this is a exocyclone that occurred in March of 2017 off the coast of Japan. So on the top here is surface winds from Cygnus. The middle is latent heat flux, and the bottom is sensible heat flux. So we see here that this exocyclone, one reason why we want to analyze this one early on, is that it stayed the low pressure center stayed within Cygnus's range for about 24 to 48 hours. So we're actually able to observe some of the features and the fluxes poleward of the warm front here. But more importantly, we're also able to observe where the large heat fluxes occur in exocyclones, and that is in this post-cold frontal sector. So we're able to see that Cygnus is indeed able to capture and observe what's happening in these regions, as well as what's happening in the warm sector. So you can see the negative heat fluxes as well going on. So this is indicating where the air temperature is warmer than the ocean. So even though that information is not coming from Cygnus, it's coming from reanalysis, we can use the wind speeds to then better estimate what's occurring in those regions then. And then a few other examples here. So this was the January 2018 bomb cyclone that occurred off the coast of the United States. So this is one example here where the cyclone formed within Cygnus's range, but quickly moved poleward outside of it. But even though it had moved poleward outside of Cygnus's range, we're still able to observe that post-cold frontal region. We are able to see those strong heat fluxes, as well as some of the negative heat fluxes in the warm sector. And then in this case here, this is off the coast of Australia, and actually just in between Australia and New Zealand. So in this case, the cyclone center actually stayed outside of Cygnus's range the whole time, but nevertheless, we're still able to observe the post-cold frontal sector. And I got to remember to flip things around in this part of the world. But yeah, we can still see the large fluxes off, thanks to the East Australia current going on here. So even though this even though these cyclones are outside of Cygnus's range, we're still able to observe what's happening around the cold front. And we can see that as well with some of our composite analysis. So the spot here shows, how often do we get expected point within 500 kilometers of the low pressure center? How often does it come within 25 kilometers of warm front and within 25 kilometers of cold front? And we see that with the warm front, because if you remember, where Cygnus is positioned, a lot of the observations are going to occur equatorward of the warm front, and you're not going to get many observations at the warm front or even poleward of the warm front. So this is why our observations of warm fronts are limited. But when it comes to cold fronts, it's much better because that cold front can extend pretty far equatorward from the ETC center. And so that's how we're able to get the observations of the post-cold frontal sector and of the warm sector as well. So, it's important to have those. I think it's important to have those kinds of observations because that's where the post-cold frontal sectors we're going to see the strongest fluxes, and the warm sector is going to be where that moisture is being transported into our cyclones, and also where the atmospheric river would be. So now that we have these observations, we show that, okay, yes, we can use, even though Cygnus is a tropical satellite, and we can use it to observe the air-sea interactions within ETCs and ARs, does this actually, provide any valuable information for how the air-sea interactions are actually impacting how these storms develop? So with this, we want to do some correlation studies and compositing all our observations of the ETCs that we've had since Cygnus was launched. And so we want to see, when the fluxes are stronger in the post-cold frontal region, do we see stronger precipitation? Do we see deeper cloud structure? And then also too, when we focus on fluxes in the warm sector, do we see similar correlations as well? Because the warm sector, again, is where the atmospheric river would be. Um, so with this, we divided, so this is a paper that we had published last year in J Climate. And we're classifying extracyclones based on weak, moderate, and strong fluxes in both the post-cold frontal region and separately in the warm sector. And what we're doing is seeing the coincident observations of the fluxes with coincident observations of precipitation and cloud structures and precipitable water. So that data is coming from iMerge, from MODIS, from AIR2, and other such sources. And so we want to see how well do stronger fluxes correlate and coincide with a stronger cyclone as well. So this is the different regions here. So yeah, so you can see that how we classify it. So this is essentially the lower third, the middle third, and the top third for each sector when it comes to these fluxes. So what we see is that when we have strong coincident surface heat fluxes in the post-cold frontal sector, we do see a stronger cyclone. So in this case here, this is the distribution of precipitation from iMerge and when fluxes are weak in the post-cold frontal sector versus when they're strong in the post-cold frontal sector and their difference. So you see that there is strong, even though there's a bit of a dip just outside of the low pressure center, overall, we do see more precipitation along the frontal regions. That was expected. And then when we look at cloud top height, again, weak versus strong, we see a higher cloud top heights, especially along where the warm front would be. And then actually lower cloud top heights in the post-cold frontal sector. So I didn't show the images here, visible imagery from geostationary satellites, but oftentimes when we see the strong fluxes in cyclones, we see more cumulus clouds forming in the post-cold frontal sectors near the boundary layer. That might be in relation to the fluxes as well. But nevertheless, we're just showing that when the fluxes are strong in the post-cold frontal sector, we see this kind of distribution of cloud top height. And of course, the higher cloud top height is, that could be an indication of stronger storms and convection going on as well. And then here, this is showing precipitable water between weak and strong cases. And these lines here are the ascent rate. So we're seeing that when the fluxes, again, are strong, the coincident fluxes are strong in the post-cold frontal sector, we're seeing stronger ascent strength within the cyclone and a bit stronger or a bit more precipitable water as well. Now, what happens, but then when we look at the warm sector, our results are a bit different, I would say. So again, we're looking again at the coincident fluxes, what's happening at that moment. And so we see that when latent heat fluxes are stronger in the warm sector, it does lead to a bit more precipitation, but not the same amount, I would say, as we see in when it's stronger in the post-cold frontal sector. And actually, when we see stronger sensible heat fluxes in the warm sector, we actually see less precipitation going on in those cyclones. Yeah. And so we see a similar distribution here when it comes to differences with cloud top height as well. So when latent heat fluxes are stronger in the warm sector, cloud top height distribution, it looks quite differently. And then also we see actually lower cloud top heights when sensible heat fluxes are stronger in the warm sector. And again, we see precipitable water decreasing, with sensible heat fluxes. And when it comes to latent heat fluxes, we see slightly stronger cyclones, but not as much as we see. And so one thing that we need to consider here is that when the coincident fluxes are stronger in the warm sector, it may actually be a sign of a weaker warm conveyor belt, because if the warm conveyor belt is strong, then you're going to be actually hopefully be having those negative fluxes, because you're having all this warm and moist air being transported over the ocean into the cyclone itself. And so ideally that would be strong, but if that's weaker, then that might lead to more fluxes. But then, it's kind of interesting to think about how that works back and forth with each other. And so this, again, if you remember earlier on when I was talking about the different papers talking about the impact of fluxes on ETCs, there was a paper or two that said that the stronger the fluxes are, the weaker the cyclone is. And maybe this is where that kind of discussion happens, because it shows It really depends on which sector you're looking at within the cyclone. So it shows that it's not quite a uniform, um, you know, we can't just definitively say that, oh, when the flux is stronger, it's going to be a stronger cyclone, because again, it could, you know, you have to remember what sector you're looking at as well and how you do this analysis. So yeah, so this is just those same plots. These are all the differences plots here. Just kind of show the correlations we're talking about. So again, on the left is the fluxes in the post-cold frontal region, and on the right are the differences when the fluxes are strong versus weak in the warm sector. So again, you see much stronger signals with the post-cold frontal sectors fluxes versus the warm sector fluxes. So what we're trying to do now is, with these plots here, what we're essentially showing is how the strong fluxes coincide with the cyclone. So it's not necessarily saying as well that these fluxes are directly leading to a stronger cyclone. But at this point, it's just pure correlation. So what we need to be able to do is actually start linking what is happening at the surface to what is happening with the cloud and precipitation structures that we see within the cyclone. So with this, this is still kind of preliminary work here. We just submitted a proposal on this with the latest CYGNSS call. What we're trying to do is, so in this case here, we're looking at a few case studies. So this is a extratropical cyclone that occurred off the coast of Japan on the December 2019. So we see these two observations are about, let's say, 21 hours apart. So we see how the cyclone, when it's starting to develop, we're seeing strong latent heat fluxes in the post-cold frontal region. And then when it matures, about 21 hours later, we're seeing much stronger heat fluxes as well. And you can actually kind of see the missing data that we have here from the QC flag because of the high winds in that situation as well. So we see that, and then this here is the cloud top height at the same time as this observation here. So this is when again, I-merge precipitation rate. So this is when the cyclone has matured. You're seeing very high cloud top heights, this is cloud top pressure, excuse me. But nevertheless, still showing that we're having very high clouds in this situation here. And then we're seeing some very strong precipitation cells along the cold frontal regions as well. So we're seeing, similar to what we saw in the composite analysis, we're seeing strong cloud top heights and low cloud top pressure and strong precipitation rates in the frontal region when we have strong coincident fluxes in the region. But now we want to be able to link it. Are these fluxes actually contributing to this increase in precipitation? Is it contributing to this increase in cloud top height? So we're starting to do a little bit of preliminary trajectory analysis here. So these are some very preliminary forward trajectories from high split. We're starting at about 10 meters above the surface in this area of the strong latent heat fluxes that we saw early on in the extracyclone as it developed. And so we see here that, where we place these is kind of a little bit of a cross shape right in the area of the strong heat fluxes. And we see that most of these parcels are following the path of the extracyclone. There's one here that goes equatorward, but we'll talk about that later, actually. And we see that the closer these parcels are to the center of the cyclone, the more likely it is to get entrained into the cyclone. And actually, we see more likely for it to have some vertical transport as well. So that could indicate, it's being transported up in time to be that energy being transported up into the storm and possibly converted into providing additional moisture and energy for the precipitation and cloud structures. And when we look at so this is, the flux is early on, and when we look at how the precipitation rate looks 21 to 24 hours later, you can actually kind of see just a little bit of a quick eye test that where these parcels end up is just around the area where that cold front is. So it's possible, it's still way too early to say. And again, we're just doing an eye test here. But there could be a link between the strong fluxes earlier on in ATC development and to the cloud precipitation structure. This is something that we still want to test. This is still something very preliminary, not publication ready, that's for sure. But then when we look at the cyclone 24 hours later, so this is when we have these strong latent heat fluxes in the post-cold frontal region. And we do the same trajectory analysis from this region keep forgetting to include where the low pressure center is here. But nevertheless, if you remember where it was, you can see that these parcels do follow where that cyclone is. And the closer the parcel is to the low pressure center, the more likely it is to follow and have the vertical transport. But if you compare where these parcels are and where the fluxes are to how the precipitation and cyclone looks about 21, 24 hours later, it's a much different story. So even though we have these strong fluxes occurring here, um, and they may be getting transported into the storm, it's not exactly translating to more precipitation or stronger cloud structure as well. So it's not exactly a one-to-one relation as we thought it would be. So it could be possible that, um, yeah, when we it's so one thing we might hypothesize is that it's the fluxes early in ETC development that might have the most impact on how on the cyclones. So even though the fluxes are stronger when the cyclones mature, those fluxes may not actually be getting entrained in time into the cyclone to actually have an impact as well. And then those fluxes could actually be transported elsewhere, as we'll discuss later. And then also, some of these other case studies here indicate that these fluxes may not be transported at all into the cyclone. So this is just a quick example from a cyclone off the coast of the United States. And we're doing the same cross pattern where these strong fluxes are, and we're seeing most of the parcels where the fluxes are actually being transported equatorward and staying close to the surface. Only one or two of these parcels seem to be following the cyclone as well. So this is something that we want to, keep investigating. But nevertheless, we want to keep looking at the flex, we want to keep looking at how fluxes early in ETC development, and as well as in atmospheric river development have a role in this because again, when the actual cyclone is matured and the fluxes are the strongest, it may not actually be getting transported into the cyclone. It may be transported elsewhere. And in this case here, we're also looking at just the post-cold frontal sector. But again, we need to see maybe do this kind of similar analysis in the warm sector because that's where the bulk of the energy is. That's where the bulk of the energy is being transported into the cyclone as well. And then as we saw in the composite analysis, we're having some differing results. But then one thing that we also want to look at is, what if we take this area, what if we look at, if we take the observations of Cygnus of the ocean surface prior to the cyclone arriving? So how does that impact the development? So what we're saying is like, okay, if we have strong fluxes in this region and then a cyclone and atmospheric river come over that same region about 24 hours later, does that lead to a stronger cyclone? Because if you're having those strong fluxes prior to development, then it's more likely to get transported into the warm sector and actually lead to a stronger storm. So this is some of the other preliminary analysis that we've done. So what we're looking at here is, as I mentioned, so this is the same sort of composite analysis, but we're no longer looking at coincident fluxes and coincident precipitation rate and cloud observations. We're looking at fluxes 24 hours before ETC and AR arrival in the warm sector, so the warm sector is where if there's an atmospheric river associated with an ETC, it would be within the warm sector. So we're seeing if the fluxes are strong, where that warm sector will be 24 hours prior, does that lead to a stronger cyclone and possible stronger atmospheric river? And in this case, we are seeing that. So when you have strong fluxes prior to the arrival, we are seeing more precipitation, more significant precipitation rate. The precipitable water doesn't change too much, but we're seeing a bit of stronger ascent strength with the cyclone. And then we're actually seeing higher cloud top heights near the cyclone center as well. And so this is, some very good preliminary work here to show that, what's happening prior to the actual cyclone and earlier on development, maybe the processes, within the air sea processes earlier on and prior to ETC genesis may be actually having an air genesis, maybe having a larger role than what we typically have looked at. But also, too, we need to be saying, is the energy from air sea interactions being transported from upstream or downstream systems? So maybe we shouldn't be looking at that individual cyclone itself, but maybe we should be looking at the broader environment as well. So we started wanting to look at this because of a very interesting paper that was published in JAS last year. So just to very briefly summarize this paper, and I'm probably doing not the best job in summarizing it, I will say. Um, they were using coamps and Lagranto. So they developed a idealized model within coamps um, and running Lagranto for trajectory analysis from this extratropical cyclone, from this primary extratropical cyclone in its post-cold frontal region. And we see that the parcels in this case, are transported upstream to the following cyclone as well. So this is over the course of about 10 to 11 days. And they reran it again, but this time with surface fluxes turned off. And we see that even though most of them are transported upstream, the upstream cyclone is actually weaker in this case. So what this suggests is that the fluxes produced in the post-cold frontal sector within this actual cyclone don't actually impact the cyclone itself, but actually end up making the upstream cyclones much stronger. And this could actually be leading to the formation of AR families and temporal clusters of actual cyclones. And so we thought this was a really great paper. And of course, similar to what we discussed earlier, when it comes to these other modeling studies that try to look at how surface fluxes impact ETCs and ARs, one thing that's needed is more observations. And so we think that this is actually a very good place for us to use CYGNSS data to start providing some of these observations, and then we can use Lagrange or high split to understand where those surface heat fluxes are being transported and see, do we see this sort of relation going on here, or is it a bit more nuanced than that? And sure enough, we actually have some very good observations from CYGNSS of the air families that impacted the West Coast United States last year. So this was from about late December 2022 through mid to late January 2023 last year. There were about 9 atmospheric rivers that formed in the Eastern Pacific and made landfall on the West Coast of the United States here. So when I mentioned earlier about our car getting flooded when we lived in Los Angeles, it was from one of these ARs. And one thing that's important to be looking, and the reason why we want to be analyzing AR families is not just because we have these observations, but because AR families are likely to cause a lot of the, provide additional challenges for infrastructure in the West Coast of the United States and other parts of the globe, because you're not having as much recovery time between events as well. And so with this, we want to be able to, because these ARs were occurring within CYGNSS's range, we can, use the flux observations to understand, how that energy is being transported between the different ARs. So this GIF here is over the course of about a month. So the black lines are integrated vapor transport from Era 5. Then the dashed lines, I don't know how well it's appearing on your screens. That's just sea level pressure as well, so you can kind of see if there's a extratropical cyclone associated with it. And the lines are latent heat flux observations from CYGNSS. So we see that in many of these atmospheric rivers, we're seeing some very strong latent heat fluxes associated with them. And important to note, I don't know if you remember the DGF plots from CYGNSS that we showed earlier, but the DGF averages in this part of the ocean is about 200 watts per meter squared, maybe 150 or 250, somewhere between 150 and 250, if I remember correctly. So we're seeing these fluxes are well above the DJF average as well for this region. So again, what we want to see is, are these strong heat fluxes that we have associated with these atmospheric rivers, are they being is that energy and moisture being transported into the AR itself, to that same AR that's associated with it? Is it being transported upstream to the following atmospheric river and maybe making that system stronger? Or perhaps is it a little bit of both? So those are the kind of questions that we want to be able to answer with the data that we have from CYGNSS. So this is just a snapshot of at 3 different times from that GIF. So the top here is December 28th at 18Z. We have a very strong atmospheric river here, about northwest of Hawaii. So we see this, the negative latent heat fluxes within the atmospheric river, as well as the strong positive latent heat fluxes west of that. Here on January 4th at 12Z, you see the strong atmospheric river about to make landfall on the coast of California. This is, and you can see with the sea level pressure observations here, this is the post-cold frontal sector, and we're seeing those large latent heat fluxes associated with that, just west of that AR. And then again here, on January 12th at 60. We actually have two atmospheric rivers here. This one's, I believe, in the process of making landfall of the west coast of the United States. And we see the large latent heat fluxes west of that. And then we have another atmospheric river here, well over the middle of the Pacific Ocean, right along the anti-meridian. And oops, click too soon. And we have, again, the large latent heat fluxes associated with that. So what we want to do, at least in this case, is again, this is still very preliminary for us, is that we're going to start the forward trajectories from this area where we see the strong latent heat fluxes and see, how those parcels are transported and does it end up being associated with the atmospheric rivers that we see here. And then again, we're going to start another high split trajectory, preliminary high split trajectory from these areas of the latent heat fluxes and see does it get transported into these ARs. And we're picking I picked these timeframes as well because the idealized modeling, their trajectory analysis was over the course of about 10 days. So roughly pick something about a week apart because high split only, at least in our analysis, high split only went up to about a week. But we just want to see, do those parcels get transported to the upstream atmospheric rivers? And we see, so we start here with these parcels or with this area of high latent heat fluxes. We see, the parcels, doing this little whirl around. So they're possibly getting, we didn't quite line it up to where the atmospheric river is, because again, this is still very preliminary for us. It's still pretty new. But we see that these parcels are being transported upstream, possibly to another atmospheric river. We see some vertical motion as well with these parcels. So even though they are close to the surface, maybe they're picking up additional energy as well, being this close to the surface for a while. That's another thing that we have to factor in before they're transported vertically into possibly an ETC or atmospheric river. So again, it's being able to analyze how how that energy is being transported. But we see kind of roughly, this again, it does get transported. It does seem to be transported up into the following atmospheric river, or one of the following atmospheric rivers, as well, that we see here. And then again, we do the same analysis from this atmospheric river in the areas of the large latent heat fluxes that we see. And the trajectory analysis here appears pretty similar to what was shown in the idealized models. So we see some of these parcels staying very close to the surface and being transported upstream, possibly to another atmospheric river. Unfortunately, gets cut off, so we don't know exactly where it ends up. But at the same time, too, a parcel just a few degrees poleward ends up going in a completely different direction. We see this green one here appears to be entrained into the same atmospheric river that an ETC that it was a part of. So this might be indicating that the additional energy here may be leading to the precipitation and cloud structure that we see within that atmospheric river in extracyclones. So what we see is that it's what any realtor or real estate agent will say: location, location, location. The location of where these fluxes are occurring will have a very different impact on the cyclone and atmospheric river. A half degree to 1 degree difference can lead to the energy from the fluxes, can lead to the parcel being transported into the atmospheric river itself, or being transported upstream to another atmospheric river about a week later or so. And then again, we'll probably also have to factor in some of these parcels, even though they're being transported, are staying very close to the surface. So maybe we have to consider, do they lose that energy that they have from the strong latent heat fluxes? Is gaining more energy as well? And how does that end up being impacting upstream cyclones as well? So again, all this is very preliminary. I'm happy to get feedback on this because, we want to keep testing this. We want to do more than just these few trajectories, have it at more locations, at more times, and just see, how does it get transported at the various time stages within the ETCs and ARs. So again, we want to continue building on this trajectory analysis. So we've been using high split. We'll continue using high split, look into using Lagranto as well. And we want to start those forward trajectories from where we have the surface heat flux observations. And we could probably be more specific about where we started. So we can take the actual specular point observations, the longitude of the specular point observations, and start the trajectory analysis from that location. And then we can also, observe how ETCs and air sea interactions impact ETC and AR development, and then also factor in ETCs with and without an AR. Do we see differences in the latent simple heat fluxes and how they interact with these synaptic systems as well? And then, of course, even though we're purely observationalist here, it might be important to start using some modeling data. So we have these idealized models that other people have done, and then maybe we can work with others to feed in the observations that we have here to better understand how it's impacting the cyclones after we do some of this trajectory analysis, forward and backward trajectory analysis as well. So this was a slide that I had in my seminar because I think it's always good to understand where we are. So I think the ultimate goal is we want the complete heat fluxes from space. And I will say that with Cygnus and what we're doing, we're maybe we're definitely not halfway there. I will be honest and humble myself and say that this is kind of using what we have. We have the wind speeds, but we're able to bring in temperature and humidity observations to estimate the fluxes. But it's still there's still some work to do. And I think what we're working towards now, what the community seems to be working towards, is getting the observations of temperature and humidity within the boundary layer and at the surface from space in all weather conditions. We have some good observations when we have clear skies, and I think there's probably some work being done with radio occultation to get those observations in the planetary boundary layer, but that's probably the next step. And I think once we have that, then we're very close to getting complete flux observations as well. And I know some of you are part of the butterfly mission, and I think that will get us right to that finish line as well as other satellite missions that are being proposed. But until we have that, I think what's important is what we could do is have this sort of synergy with other missions as well, because scalerometers are also poised to give us estimate the fluxes for now while we still have them, until we have those full observations of fluxes from space. So this is an example here of some other work we could do with other satellite projects as well. So this is the black swats are Tempest D observations that were on ISS. This is to represent the area that we have where COVER is observing. I know that data is not publicly available yet. So this is just a demonstration with existing publicly available data to show, can we use these observations together to understand what's happening at air sea, what's happening at the surface. So we see the lines from Cygnus when and on these days here, the observations from Cygnus and COVER don't quite overlap, at least in the North Atlantic region. But we see that, Cygnus can provide a full day of coverage in the tropical and subtropical oceans, and then observations in ISS like COVER can then provide full day observations in the mid latitudes as well. So using these two products together can really help fill in some of the gaps that we have. So yeah, to quickly summarize, even though Cygnus is a tropical mission, we do have decently reliable observations of latent simple heat fluxes over the tropical and subtropical oceans. We're able to use these observations to understand how coincident fluxes within cyclones correlate with stronger precipitation and stronger cloud structures when the fluxes are strong in the coastal from those sectors, but coincident fluxes in the warm sector does lead to different results. But we're able to then start to link these together. And we see that, when the fluxes are strong early in development, it's more likely to have an impact on the development of the cyclone. Whereas when the cyclone has matured, and even though the fluxes are stronger, it may have little to no impact on that cyclone itself, but it may actually be impacting upstream systems as well. I think I just said this as well. I do want to wrap up quickly because I know we're almost out of time. What we want to do now is, also look at how the air-sea interactions within a primary ETC and AR are impacting, the environment in the upstream cyclones and atmospheric rivers. And so I think there's a lot of work to be done here. And I think observations from satellites like Cygnus can provide some of the key data to be able to do this sort of analysis. So with that, thank you so much for for listening to me blabber on. If we don't have time to ask any questions, I'll be at EGU and hopefully at the Ocean Vector Winds meeting in Salt Lake. So maybe we can chat there as well.
Well, thank you very much. And questions for Juan? If I can start by asking a basic question, are the Cygnus data on the GTS, is ECMWF able to assimilate them?
That is a good question, and one that I do not know. I know that the Cygnus data, I know that's publicly available through NASA
Mhm.
Earth data and the PODAC. So I don't know if it's already with ECMWF. That would be, yeah, that's something I do not know, but hopefully it should be.
Is there near real-time product?
There is not yet.
So
I know that's
probably they're not getting them then.
yeah, because yeah, last year there was a joint Cygnus and Tropics applications meeting, and every time someone was, reality is that the Cygnus satellite was never meant to be operational or
Mhm.
near real time. It's just meant for research purposes. Um, and really, yeah, because I think the money is just not there, from what I understand, to be able to download the data every single time it comes over a ground
Mm.
station.
Common problem, I think.
Yeah.
Christine has her hand up.
Hi, thanks very much for this really, really exciting work. Very well done. I can answer the question about ECMWF. They don't currently assimilate Cygnus data, but they are thinking about it. So it's something which is currently being looked at. So I had a question about, particularly to illustrate the value of these Cygnus measurements being made at much higher temporal frequency than you would get from other sensors. If you've had a chance to check, because you've got these in situ measurements of heat fluxes,
Mhm.
and whether you'd quantified the kind of the benefit of doing the heat flux estimation with the Cygnus winds as opposed to
Mhm.
using the ERA5 winds. Is it something you've looked at, and has it shown any kind of improvements or benefits from doing that?
We have done some preliminary work there. So I think, but in terms of like actually producing, I, so I think we've done that for some of the validation work that we've done, if I remember correctly. Um, I know I have those plots somewhere, and I did not include them as a
You,
supplemental slide. And and I don't want to I don't want to accidentally misspeak and
No, no,
say,
no, no. It's okay. I'm not expecting you to show me because it was such a small part of a wonderful presentation. I don't want to pick you up on that, but
it's
I was
okay.
just curious because it's a great data set that you have, and there'll be, I come from the satellite world. It's always this kind of setups where you get the evidence about the value of these observations.
Right.
And if I may just ask a second sort of follow-up questions, is whether you were considering looking at how these heat fluxes might vary during the day. I mean, because you have got measurements in different times of day, that's
Yes.
something that you have done or planning to do.
There is, so I'm pausing my sharing screen. I don't remember if I included, no, I did not. Um, of course, I had those kind of plots, the two questions that you have, and of course, I did not have them in my slides. Um,
Not to
yeah,
worry.
I did. Well, okay, I did present something similar at AMS. Um, okay, this is bothering me, but yeah, we are looking at of including um, local solar time at every single speculative point. Um, and that would be able to then, give us some diurnal, um, be able to understand some of the diurnal impacts of the fluxes as well. So yeah, that is definitely something that we want to be um, definitely looking at in the
Yeah,
future. It
that'd
is,
be
here we go. Here
that'd
we
be
go.
really interesting. Yeah.
Yes. So I hope this is allowed to show a slide from that. So this is something very preliminary. I did a very brute force estimate of local solar time at every single speculator point. And yeah, so we see, so this is, local solar time midnight across the globe, plus or minus 3 hours, and then local solar time at noon, plus or minus 3 hours. I don't remember if this is for the whole year, the whole data set, or just this might just be DJF as well. So it's kind of hard to see, but if I remember correctly, yeah, you can see some of the differences in the flux, especially in the Kuroshio
Hmm.
extension region here. You see some
Right.
differences as well. So yeah, so this is something that we want to be
Great.
including in future Flex
Mhm.
products as well.
Yeah, that's really exciting. Yes, thank you. That's brilliant. Thank you.
So, and then Benjamin Barr has a hand up.
Hey Juan, really nice work. Um,
Thanks.
so I know that Cygnus was sort of originally conceived for like kind of mature, strong tropical cyclones, and
Hmm.
now you've also shown this extension to extratropical cyclones. But there's certainly a lot of other tropical phenomenon that happen kind of in the lower wind speed range where I think this could be
Yes.
useful, right? So just tropical cyclogenesis on its own,
Hmm.
Haddon-Julian oscillation, things like that. Can you give some context about how this product and its kind of unique capabilities and coverage could help fill in some gaps for that kind of stuff?
Yeah. So Eric Maloney's group at and almost at the wrong state at Colorado State has done work on and using our Flex product and understanding what's happening within the NJO as well as the Eastern Pacific regions as well. So they had a paper in 2020 from Bowie et al. I think. Um, seeing the correlations to how fluxes correlate with changes in precipitation in the over the tropical oceans as well. And I can maybe find a link here. I should have had these prepared. I did not, um, but yeah. So that is definitely. Here we go. Let me resume sharing. So yeah, this is one of the papers from their group. So they're using the Flux product here. Um, And yeah, so which one is yeah? So this part here, this is latent heat. This is how latent heat flux correlates with precipitation
Mm.
um, over the Indian Ocean and Western Pacific. So yeah,
Mhm.
that's one example of how this product's been used.
Nice. Well, thanks a lot. Very nice work.
Thanks.
And then there's a question from Rick Danielson in the chat, or a comment maybe. It would be nice to associate trajectory, origin, path, and latent heat release wherever possible, and maybe distinguish sensible heat flux and latent heat flux roles as a function of season. So I guess there's a question, have you thought about seasonality and the roles of these?
Yes, so it's definitely something we want to be looking at. So I will say a lot of this work that we've done, we've kind of led me on the path of air-sea interactions and how that impacts latent heat fluxes from it kind of stemmed from this paper that we had in monthly weather review when I was in grad school. So this is cloud side observations with a warm front. So they're about 36 hours later. So this is the same warm front, and we're starting to see some of the convective styles within the warm front. So two of the hypotheses that we led to this being one was looking at the actual latent heat release within the warm front itself, and then air-sea interactions. So I went down the path of air-sea interactions, but I think we might need to also look at um, the latent heat release as well within the environment within these clouds and precipitation jugs and how all of these are related because it's just a very nuanced sort of question.
Mhm. Great. Well, thank you very much. I think we're pretty much at the end of the hour. So unless anybody has a last desperate question, I'll encourage you to contact Juan separately. And thanks, Juan, for a great presentation. And thanks, everyone, for being here.
Thank you.